For today, we are going to be going over acceleration. What I go over today is going to be a review from Science 10. All right, I'm not going to get into many of the new formulas today. We'll probably cover those on the Monday after the break, which will be a good way to review what we talked about today, because you're going to forget it all. You have a week off. Yeah. All right, so we need to understand what accelerated motion is, or basically what the definition of acceleration is. And acceleration is any change in velocity over time, okay? Or it is the rate of change of velocity over time. Anytime the velocity of an object is changing, the object is accelerating, which is why in physics we do not use the term decelerate, okay? Decelerate is a negative acceleration. Any change in velocity is acceleration. All right, we're going to learn the relationship between change in velocity, distance, time, and acceleration. That's basically, look at the new formulas you're going to use, which is basically just algebra. Right? It's not that they're, going to do anything crazy. They're just new formulas you have to know how to use. And be able to solve accelerated motion problems. The big thing here, guys, is write out your givens, because they will help you to choose which of the 5 acceleration formulas you should use. Right? Last year you only had one, so it was easy. If an object was accelerating, you knew you had to use that formula. Now you have to look at what you're given. Just because an object is accelerating doesn't mean you use Vf minus Vi over t. Right? You might use something else. So there's the definition of acceleration. I stated it earlier. Whenever the velocity of an object is changing, we say the object is accelerating. Okay? The meaning of average acceleration, or more accurately, uniform acceleration, is best illustrated by a plane taking off or an object falling, okay, or something like that. But most objects that we would deal with do not exhibit perfectly uniform acceleration. Okay? Lots of people say, oh, a great example of uniform acceleration is a car accelerating away from a stoplight. Except that that's one of the worst examples of uniform acceleration, because it's not uniform at all. Okay? A car has a velocity versus time graph when it's accelerating away from a light that looks like this. Is that uniform? Why does a car's velocity versus time graph look like that?
Because you go to the speed limit and don't go any further.
Okay, assuming I don't care about speed limits. I mean, eventually, this does flatten out, but not because of the speed limit, because I'm a lead foot, but because I hit the top speed limiter. Most cars have an electronically limited top speed such that they cannot overrun the rating of their tires. So, get cars with good tires. It's usually involve cars with lots of horsepower and fun. Okay. So their graph looks like this. It flattens, and it's because cars have what? Not tires. Not doors. Gears. Yeah. I know you're probably thinking my car's an automatic. It still has gears. Okay? And I realize that standards are going the way of the dodo. Okay? Every year when I ask how many of you can drive a standard, the number of hands that goes up goes down, 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 because they hardly even make them anymore. Okay? But all cars have gears. Even if you have like a hybrid car, it may still have a continuously variable transmission, which still involves changing gears. The only cars that wouldn't have gears, electric. Yeah. Okay? If you have a purely electric car like a Tesla, okay, it's going to have just the electronic motors that go fast. So its acceleration will be a little bit more uniform, but it's still not going to be perfectly uniform. Okay? So even with an electric car, as you go faster, the amount of air resistance increases, because the faster you try to go through the air, the more the air resists you. Right? So even with an electronic car that would normally, if it was doing it in a vacuum, would have a perfectly linear graph, is going to start to plateau, okay? Because it is going to reach the speed where the electric motor simply can't turn any faster. All right, so this is not an example of uniform acceleration. A car, typical car, has gears, and each gear does not pull as hard as the gear before. Okay, and we have gears so that we can achieve, better top speed, but also better fuel efficiency when we're going fast, okay, as opposed to needing a lot of torque down low, right? And if you kind of watched how car development has gone over the last 10 or 15 years, like when I was a kid, if you had an automatic transmission in your car, it probably had 3 gears, right? First, second, and third. You put it in drive, and that was it. Okay. Even the 1980s Honda Civics had a 2-speed standard. It was really easy to learn how to drive those. There was first and go, and that was it. Okay. And they would go from 0 to 60 in about 2 weeks. So they flatten out. The gears make that happen. Okay? And if you have a standard transmission vehicle that you know how to drive, you know you have to change the gears to produce different amounts of acceleration. The first few gears accelerate really strongly, and the last few gears don't. Okay? They're more for fuel economy and top speed, as opposed to pulling and acceleration power. That's why if you pass somebody on the road, okay, whether you drive a standard or an automatic, you gear down when you pass. Okay, if you drive an automatic, you just press the pedal to the floor, and you can feel the engine revs go up because the engine gears down, reaching for one of these gears that's lower, okay, for greater acceleration. If you drive a standard, it's painfully obvious. If you pull up past somebody and do not shift down, you'll die. Okay, because you'll put the pedal to the floor and nothing will happen. Okay, you'll be in 5th or 6th, and the car will just go. And yeah, you don't want that when a semi-truck is oncoming. Okay, so you definitely want to gear down before that. All right, does that sort of make sense? All right, this is what you learned last year in terms of acceleration formulas. That A equals VF minus VI over T. It probably wasn't written horizontally, okay? It was probably written like this. Okay, or delta V over delta T. Okay, it's also written that way. Okay, I think it's actually written that way on your formula sheet this year. All right, now where does this formula come from? We talked about this back when we were talking about velocity versus time graphs. Oh, spoiler alert, that's where it comes from. Okay, if I have a linear velocity versus time graph, okay, obviously I have velocities on the y-axis, I have times on the x-axis, so this here would be B, right? That would be Y, that would be X, and this is M. Follow me there? Okay, so if I calculate M, Y minus B over X, okay, Y is my final velocity, B is my initial velocity, or velocity at time 0, and X is time. All right, so this ends up being VF minus VI over T. That's where that formula you've been using comes from. It is the slope of the line on a velocity versus time graph. Okay, is it relatively easy to use? Okay, questions there? All right, so if we have this situation here, we got a plane taking off. A plane is a much better example of uniform acceleration because it doesn't have gears. Okay, just push the throttle forward, it's relatively aerodynamic, its acceleration is quite linear. And if you've ever ridden on a plane, okay, the takeoff you can feel it accelerating, but the acceleration is much different than in a car. So plane in the picture starts from rest, and that is an important term that we have to get used to hearing. Okay, rest means not moving. So if something starts from rest, VI is 0. If it comes to rest, VF is 0. If it comes to rest, okay, that means it's slowing down to a stop. Right? So anytime you see the word rest, one of the velocities is 0. Okay? Either initial or final, depending on the context. Starts from rest, VI is 0. Comes to rest, VF is 0. Okay. All right, so the plane accelerates down the runway and after 29 seconds attains a velocity of positive 72.2 meters per second, where the plus sign indicates the velocity points to the right. Determine the average acceleration of the plane. All right, so what I was given, VI, right? I was also given VF. And I was given time. And asked to find acceleration. Can I use my science 10 acceleration formula here? Okay, just plugging in the numbers. I don't have to manipulate here. Right, I'm just solving for acceleration. All right, so looks like this, and that means that our acceleration is 2.5 meters per second squared. All right, what do those units really mean? When I say meters per second squared, I really mean meters per second per second. Right? How many meters per second am I changing my velocity by each second? Okay? We just call that meters per second squared because it's quicker to say and because it's also mathematically true. Right? If we're looking at fractions here, okay, meters per second would be on the top of this formula, right? Meters per second and dividing by seconds. Okay, that's the same as dividing by seconds over 1. Everyone okay with that? Okay, what do we do when we divide fractions? Flip and multiply. Meters times 1, meters. Seconds times seconds, seconds squared. Okay, so meters per second is also mathematically meters per second squared. Does not mean your number is squared. Okay, I see people do that all the time. It's not right. Okay, just the units. Okay, the seconds. All right, so that means the velocity of the plane changes by 2.5 meters per second every second. Okay? And you would feel that. Okay, you would feel pushed back into the seat. Okay, a little bit as the plane accelerates, because 2.5 meters per second squared is about 1/3 of gravity. So it would feel like someone who weighs 1/3 what you weigh standing on your chest. Okay. So you notice that. Okay, you feel pushed into the seat. All right, questions on how that works? Everybody's good with using that formula? All right, these are our other formulas. Okay, these are the other 4. So this one here, D equals VI times T plus 1/2 AT squared, and the second one, VFT minus 1/2 AT squared, they both solve for displacement. And they are also derived from a velocity versus time graph. Okay, thinking back to graphing, let's say I have a velocity versus time graph that looks like that. How would I calculate the displacement? How do I get displacement from velocity time graph?
You find the area of
Yeah. Right? You find the area under the line, right? Because that's average velocity times time. All right. So this is, let's just say that this is the equation for this formula. Y equals 5.2x plus 1.5. So that means this value right here is 1.5. Everybody all right with that? Okay, let's say this happens for 10 seconds. And okay, let's say this number up here, so 52, 53 and a half, so 53. Okay, so I would calculate the area under the line. So how do I calculate this part here? It's a rectangle. Base times height. So that would be this number times that number. Everybody okay with that? Okay. Since this is how fast the object is going at time 0, it's also my, my initial v, so vi. So this number is vi. And I'm multiplying it by time. I'm doing that, vi times t. Okay? When I calculate the area of this rectangle, I'm going base times height divided by 2, which is actually a manipulation of this. So this formula calculates the area under the line. And its sister formula does the same thing, but it does the reverse, where this formula finds this area, this formula finds this whole area, and then subtracts this. Hey,
I
what?
just need to check something on one of the Chromebooks that I can't go in right
Okay.
now. Don't mind.
Okay, so if I go VF times T, I'm taking this number here and multiplying by this number. I'm going base times height. I'm finding this whole rectangle right here. Everybody okay with that? And then I'm subtracting 1/2 AT squared. Well, is this triangle and this triangle here, are they the same? Yep. So if I subtract 1/2 AT squared, I'm essentially calculating this whole rectangle and then subtracting that part. Still leaves me with the same thing. Right? So they both calculate the area under the line. But way more easily than actually calculating the area under the line, the way we've been doing it. So if I was to give you a graph like this on a test, with that equation, could you use these two or one of these two formulas? You could, and it would be really fast, and it would be correct on top of it, okay, to do so, to calculate the total displacement. All right? Now, the trick here is recognizing where do I get these numbers from. VI is B. T is whatever length of time the graph is telling you to use. All right? And acceleration, well, slope of the line. Right? All those numbers are in the equation for the line. All right. Okay, so those two do that. Okay, this one here is not really a graphing thing, but it's pretty handy if you don't know how long the object is accelerating for. Okay, it allows you to calculate either VF, VI, A or D without needing time. So if you have both speeds, okay, and the distance, you can calculate the acceleration. Right? You just have to remember that VF and VI are squared in this formula. And then this formula we don't use as much. And the reason we don't use it is it requires the acceleration to be perfectly uniform. These other ones don't necessarily, but this one does. And the reason it does is because this is really all it is. As long as my acceleration is uniform, I can add my final and initial velocities and divide by 2. Right? That's how we learned to calculate averages when we were smaller. Okay? And it works provided the acceleration is uniform. Okay? And then we just multiply that by t. So you can use that one, but it's the one we use the least. Okay? If a question like outright said, an object experiences uniform acceleration and then gives you these numbers without acceleration, you could use that together. All right, so let's do this one together because it's kind of review from before, okay, from Science 10. So I'll have you just write that one down real quick and give it a try, see if you can do it. So for this one, we have a hybrid car with an initial velocity of 10 meters per second east. So they gave me VI. 10 meters per second east. And it accelerates at 3.0 meters per second squared east. What did they give me there? They gave me the acceleration. All right, how long will it take the car to acquire a final velocity of 25 meters per second east? Okay, everything's east, so everything's positive. I don't have to worry about anything on that, but it is something you have to watch for on other questions. Okay, for example, if a car is going up a hill and runs out of gas, its initial velocity is up the hill, but its acceleration will be down the hill. Once it runs out of gas, it's not pulling up the hill anymore. Okay, gravity is going to start bringing it back down. So we have to watch for things like that. So we're looking for how long it will take. So we're solving for t. So we got to do a little manipulating here. A equals VF minus VI over t. This is just algebra, so nothing you guys can't handle. All right. If I want to solve for t, I need to move it over to this side first by multiplying both sides by it, and then dividing both sides by a will bring acceleration back over there. Okay. So time will equal 25 minus 10 over 3, so 15 over 3 should be 5.0 seconds. Okay, will be our time. Everybody all right with that? So, not a hard formula to use. You guys have been using it already for almost a year. All right, both of these questions involve that same formula. They're just going to ask you to calculate different things. Watch out in question number 2. Can you use kilometers per hour and meters per second squared in the same formula? How do you convert kilometers per hour to meters per second? Okay, let's have a look at that real quick. So let's say I've got something, let's say I've got this, the 20 kilometers per hour. And I want to convert that to meters per second. I have to do what's called a compound conversion. That is, change both the distance and time units. So first thing I want to do is change the kilometers to meters. What do I multiply kilometers by to get meters? 1,000. So there are 1,000 meters in 1 kilometer. I just multiply by the conversion factor. Now there's kilometers on the top and kilometers on the bottom. What will happen to them? Right. All right. Now I have 20,000 meters per hour. That's the same as 20 kilometers per hour. Agreed? But I don't want meters per hour. Nobody talks like that. So I need to convert the hours to seconds. In 1 hour, how many seconds are there? Everybody's like gut reaction, knee-jerk reaction. 60. 60 minutes. 60 seconds in a minute, 60 times 60, 3,600 seconds. All right, now there's hours on the bottom, hours on the top, and what I end up with is I take whatever's in meters or in kilometers per hour and I multiply it by 1,000 divided by 3,600. Now, I'm going to simplify that even more. Can I reduce this down? Okay. I can reduce it so it looks like this, right? Same ratio? What's 20 times 1?
20.
Okay, so take whatever you got in kilometers per hour and divide by 3.6. That will convert your kilometers per hour to meters per second. And the reverse would be true as well. Take whatever you have in meters per second and multiply by 3.6 and it'll get you kilometers per hour. Okay. That's probably one you just want to have in the back of your head. All right, give you a little bit of time to try those two. was recording the whole time. Oops. All right. Let's have a look at the first one here. So, motorcycle has an initial velocity of 6 meters per second east. So they just told us VI. And it's nice when a question outright says it's the initial velocity. You're not going to get that very often. Okay? It's not going to be that explicit for you. Okay. Accelerates at 4 meters per second squared east. How long does it take the motorcycle to reach 36 meters per second east? So just like the example we just did. All right, we've got A equals VF minus VI over T, and we are trying to solve for T, so we simply multiply both sides by T, divide both sides by A, and we'll have 36 minus 6 divided by 4, which should come out to 7.5 seconds. Okay, everybody okay with that one? All right, how many people have done the second? Flip that one to that. Okay, so on number 2, we've got this elk moving at 20 kilometers per hour. Okay, so we've got, what is 20 divided by 3.6? 5.5 repeating. All right, so our initial velocity is 5.5 repeating meters per second. Okay, it's accelerating, and that's north. Right, that beside it, north. Okay, and it's accelerating at 1.5 meters per second squared, north, for 9.3 seconds. What's its final velocity? And it wants it in kilometers per hour, so we'll have to convert it back after. All right, so I got A equals VF minus VI over T. So this manipulation is a little bit trickier. We have to use all 3 rules of algebra. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other, and move what's not attached first. Okay, so looking at this formula, I'm trying to solve for VF. What's not attached to VF? T. So move it first. Okay, so I'm going to multiply both sides by T, and then what am I going to do with VI? Add it. Okay, and that should make sense. This calculates the change in velocity. T times A calculates the change in velocity. So if I take my initial velocity and add it to the change in velocity, I should get the final velocity. It's kind of like when you go to work in the morning. You have no money. And then you go to work, and at the end of the day, the change in money is how much money you have at the end of the day. Okay, so the F. All right, so we've got, what was our initial? 5.5 repeating, right? Okay, plus 9.3 times 1.5. All right, when we do that, we should get, I don't want to get meters per second here. Oh, God, I hate it when it does that. Just go where I want, don't think. Okay, so 5 point, let's do that. That's not as accurate, but it'll do for now. Okay, plus 9.3 times 1.5. All right, so 19.5 meters per second, but I gotta multiply that by 3.6 to get the meters per sec, or the kilometers per hour, 70 kilometers per hour. Okay, everybody good with that one? Hopefully that all looks familiar because you would have been asked to do calculations like that last year in Science 10. Okay, I said I was going to try and eke out a little bit of time for you to work on your vector assignment. So rather than start the next formula, because I won't get it finished, you can have the last 12 minutes to work on your vector assignment. Yeah.